How fast are reactions going in a battery? And what is the relation to the power, the capacity, the lifetime and the safety? Often reactions happen with growth of material at the electrodes of the battery, such as in lithium-ion batteries and lead-acid batteries. Can we prevent inhomogeneous formation of material on these electrodes, as happens, for instance, during formation of frost on a cold winter day? These needle-like structures, dendrites called, are detrimental for the working of the battery in the end. Each battery, including the fuel cells and capacitors, have their own energy density and power density. Fuel cells have a huge energy density, but a low power density, in contrast to capacitors, which have a huge power density and a low energy density. Batteries are somewhere in between, and it depends strongly on the kind of chemistry the battery has, what the actually energy density and power density is. Such an energy density versus power density diagram shows how fast the system can be discharged to provide power. Capacitor may work in seconds, whereas batteries work in hours. These diagrams are usually called a Ragun plot. This plot shows the energy density against the power slightly differently. It includes basically already the energy density at work, which means that with the demand for high power, the expected energy density decreases. This is what we would like to figure out. Why does the energy density drop once we ask for more power? Zooming in into a lithium-ion battery performance, we see this power is typically referred to as the C rate, which stands for the number of hours the battery delivers its capacity. A C rate of 0.1 then stands for a discharge time of 10 hours, a 0.2 C rate for 5 hours, a 1 C rate for 1 hour, a 2 C rate for 30 minutes, and a 5 C rate for 12 minutes. The drop in the voltage, because of the higher power of the battery delivers, has to do with the internal resistance of the battery and is related to the kinetics of the reactions that occur in the battery. This is what we would like to figure out. Why does the energy density, the capacity, drop once we ask for more power? However, the loss of capacity does not have to be permanent, but can be recovered in later cycles at lower C rates. But a certain degree of capacity loss cannot be avoided due to degradation of the electrode materials, the electrolyte, or the current collectors. Imagine that you are working in a building at the second floor with several colleagues. Once it is lunchtime, you all go to the canteen, which is in another building across the pedestrian area. There is a little summer breeze and the sun is shining. Now think about what you experience in terms of flow of people going to the canteen. You stand up and you walk to the elevator, escalator or steps to go down. There people pile up. You arrive in the atrium or central hall and leave the building through a door. Again, people pile up. The sun is shining and there is a little breeze, so you're looking for your hat and sunglasses. People are accumulating just outside the door and moving slowly to the middle of the street. There are people moving easily to the other side of the street till they arrive at the other building. People are taking off their hat and sunglasses, which takes some time. Then they must go through a door to get into the building. Once they are in the building, they must find their way to the canteen. And finally, when they are in the canteen, they must line up for the buffet and cashier. This is exactly what ions also experience once they go from one side to the other. We can see this behavior, for instance, in a lead-acid battery. The lead-acid battery operates from two redox reactions taking place at two lead plates, both with a sulfuric acid electrolyte. When we discharge the battery at the negative electrode, lead is oxidized to lead sulfate. This means lead is reacting with sulfate ions that need to come from somewhere and hence needs to migrate towards the lead surface. Here it reacts to form the lead sulfate, and this can be grown as needles, dendrites so to say, but also as a nice smooth layer. This all depends on the migration kinetics and the rate of the reaction, something we will see later on. At the positive electrode, a similar kind of reaction occurs. Here lead oxide is being reduced to lead sulfate, and here too sulfate ions need to migrate towards the electrode, leading to similar issues with respect to lead sulfate growth. This growth all depends on the migration kinetics and the rate of the reactions, something we will see later on too.